In electrical installations, ensuring sufficient bonding of service equipment is crucial for safety. This involves creating a low-impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Let's consider a scenario involving a 100-amp service installation for a residential garage, where the inspector noted a lack of raceway bonding. The meter and panel are back-to-back, connected by a 1 and 1/2-inch threaded nipple with 4 lock nuts. The question arises whether this configuration sufficiently bonds the service equipment, considering that concentric knockouts were not used. National Electrical Code Section 250.92b2 addresses this issue, stating that threaded couplings made wrench-tight are permitted. However, the subsequent paragraph mentions that standard locknuts are not allowed. So, are grounding locknuts necessary in this case? According to 250.92b2, threaded couplings made up wrench-tight with a conductive coating are permitted for bonding service equipment. This means that the 1 and 1/2-inch threaded nipple, when properly tightened, can provide a sufficient bonding path. Now, let's consider 250.92b3, which states that standard locknuts are not permitted for grounding purposes. While the locknuts used may not be specifically listed as grounding locknuts, they are still conductive. This conductivity allows them to satisfy the requirement in 250.92b2 for a conductive coating. The use of grounding locknuts is not explicitly mandated by the code. However, they do offer an added level of assurance in establishing a reliable, low-impedance grounding path. Should you prefer to use grounding locknuts, they can be installed in place of the standard locknuts. Based on this analysis, the bonding achieved using the threaded couplings and standard locknuts can be considered sufficient, provided the connections are wrench-tight. Nonetheless, for enhanced safety and reliability, it is advisable to consider installing grounding locknuts if feasible. The primary objective of bonding is to create a low-impedance path for fault current. This ensures that in the event of a ground fault, the fault current can quickly return to the source, tripping the overcurrent protective device and minimizing the risk of electrical shock or fire. Firstly, grounding locknuts typically have a sharper edge or teeth designed to bite into the enclosure, providing a better electrical connection. Secondly, they are often made of materials with high conductivity compared to standard locknut. Thirdly, grounding locknuts are usually listed for grounding and bonding purposes, providing assurance that they meet specific performance standards. While standard locknuts may provide adequate conductivity in some situations, relying on them solely for grounding may not be the best practice, especially in critical applications or where there is a high risk of corrosion or loosening of connections. Therefore, it is generally recommended to use grounding locknuts or other listed grounding fittings to ensure a reliable and code-compliant grounding connection. Now let us consider the different types of grounding and bonding methods. Grounding and bonding are essential practices in electrical systems to ensure safety and prevent electrical shock hazards. They provide a low-impedance path for fault currents to flow back to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly trip and to energize the circuit. Firstly, grounding refers to connecting the electrical system to the earth, typically through a grounding electrode such as a ground rod or metal water pipe. This provides a reference point for the electrical system and helps stabilize voltage levels. Secondly, bonding, on the other hand, involves connecting all metallic parts of the electrical system together to create an electrically continuous path. This includes metal conduits, enclosures, equipment frames, and other non-current carrying metal parts. There are several methods commonly used for grounding and bonding in electrical systems. One method is to use a grounding electrode conductor, which is a conductor that connects the grounding electrode to the electrical system, typically at the service entrance. This conductor provides a direct path for fault currents to flow to the earth. Another method is to use equipment grounding conductors, which are conductors that connect the non-current carrying metal parts of electrical equipment to the grounding system. These conductors provide a path for fault currents to flow back to the source, allowing overcurrent protection devices to trip. Bonding can be achieved by using various types of bonding connectors, such as bonding bushings, bonding jumpers, and bonding locknuts. These connectors ensure that all metallic parts of the electrical system are securely connected together, creating a continuous electrical path. Additionally, metal conduits and raceways can be used for bonding, as long as they are properly connected and provide a low impedance path for fault currents. The National Electrical Code, NEC, provides detailed requirements for grounding and bonding in electrical systems. These requirements specify the size and type of grounding and bonding conductors, as well as the methods for connecting them. It is important to follow the NEC requirements to ensure that the electrical system is properly grounded and bonded, and to minimize the risk of electrical shock hazards. Proper grounding and bonding are critical for protecting people and property from electrical hazards. By providing a low impedance path for fault currents, they help to quickly de-energize faulty circuits and prevent electrical shocks. Therefore, it is essential to understand the principles of grounding and bonding, and to follow the NEC requirements when installing or maintaining electrical systems. When it comes to grounding and bonding, there are several common mistakes that electricians and homeowners often make. Avoiding these mistakes is crucial for ensuring the safety and proper functioning of electrical systems. One common mistake is improper grounding electrode selection or installation. The grounding electrode, such as a ground rod or metal water pipe, must be of the correct size and material, and it must be installed in accordance with the NEC requirement. Another common mistake is using undersized or incorrect grounding and bonding conductors. The size of these conductors must be appropriate for the size of the electrical system and the amount of fault current they may carry. Using undersized conductors can result in a high impedance path, which can impede the flow of fault current and increase the risk of electrical shock. Another mistake is failing to properly bond metallic parts of the electrical system. All metallic parts, such as metal conduits, enclosures, and equipment frames, must be securely bonded together to create a continuous electrical path. Failing to do so can create a shock hazard, as these metallic parts may become energized during a fault condition. Another common mistake is improper use of grounding and bonding connectors. These connectors must be properly sized and installed to ensure a secure and low impedance connection. Using incorrect or improperly installed connectors can result in a high resistance connection, which can impede the flow of fault current. Additionally, it is important to avoid using dissimilar metals for grounding and bonding connections, as this can lead to corrosion and a loss of conductivity over time. For example, using aluminum connectors with copper conductors can result in galvanic corrosion, which can weaken the connection and increase resistance. To avoid these common mistakes, it is important to have a thorough understanding of the NEC requirements for grounding and bonding. It is also important to use high-quality grounding and bonding products, and to follow the manufacturer's instructions for installation. Additionally, it is a good idea to have a qualified electrician inspect the grounding and bonding system to ensure that it is properly installed and functioning correctly. By avoiding these common mistakes, you can help to ensure the safety and reliability of your electrical system and minimize the risk of electrical shock hazards. Now let's talk about grounding electrode systems. A grounding electrode system is a network of interconnected grounding electrodes that provide a path for fault currents to flow to the earth. It is an essential component of an electrical system, as it helps to protect people and property from electrical shock hazards. There are several types of grounding electrodes that can be used in a grounding electrode system, including ground rods, metal water pipes, and concrete encased electrodes. Ground rods are typically made of copper or copper-clad steel, and they are driven into the ground to provide a connection to the earth. Metal water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet and are electrically continuous. Concrete encased electrodes, also known as U for grounds, are typically made of bare copper wire or rubber that is encased in concrete. These electrodes are very effective at providing a low impedance path to the earth, and they are often used in new construction projects. In a grounding electrode system, the grounding electrodes are interconnected using grounding electrode conductors. These conductors must be of the correct size and material, and they must be installed in accordance with the NEC requirements. The grounding electrode conductors provide a path for fault currents to flow from the electrical system to the grounding electrodes. The grounding electrode system must be properly sized and installed to ensure that it can effectively handle fault currents. The size of the grounding electrodes and conductors will depend on the size of the electrical system and the amount of fault current they may carry. It is important to consult the NEC for specific requirements on grounding electrode system sizing and installation. In addition to providing a path for fault currents, the grounding electrode system also helps to stabilize voltage levels in the electrical system. By providing a connection to the earth, the grounding electrode system helps to equalize voltage potentials and prevent voltage fluctuations. This can help to protect sensitive electronic equipment from damage due to voltage surges or dips. Maintaining a grounding electrode system is important for ensuring its continued effectiveness. Grounding electrodes should be inspected periodically to ensure that they are in good condition and are providing a low impedance path to the earth. Grounding electrode conductors should also be inspected to ensure that they are securely connected and are not damaged. If any problems are found with the grounding electrode system, they should be promptly repaired to ensure the safety and reliability of the electrical system. A properly designed and maintained grounding electrode system is essential for protecting people and property from electrical hazards. By providing a low impedance path for fault currents and stabilizing voltage levels, the grounding electrode system helps to ensure the safe and reliable operation of the electrical system. Now let us consider the effects of corrosion on electrical connections. Corrosion is a natural process that occurs when metals react with their environment, leading to deterioration and degradation. In electrical connections, corrosion can have significant and detrimental effects, compromising the performance, reliability, and safety of electrical systems. One of the primary effects of corrosion on electrical connections is increased resistance. As corrosion products form on the surface of the metal conductors, they create a barrier that impedes the flow of electrical current. This increased resistance can lead to voltage drops, power losses, and reduced efficiency of electrical equipment. In severe cases, corrosion can cause a complete open circuit, interrupting the flow of electricity and causing equipment failure. Another effect of corrosion is reduced mechanical strength. Corrosion can weaken the metal conductors and connectors, making them more susceptible to breakage or failure under mechanical stress. This can be particularly problematic in environments where electrical connections are subject to vibration, thermal cycling, or physical abuse. Corrosion can also lead to loosening of connections, as the corrosion products can expand and contract with temperature changes, causing the connections to become loose over time. This can further increase resistance and reduce the reliability of the electrical system. Corrosion can also promote galvanic corrosion, which occurs when two dissimilar metals are in contact in the presence of an electrolyte. In this case, one metal acts as an anode and corrodes preferentially, while the other metal acts as a cathode and is protective from corrosion. Galvanic corrosion can be particularly severe, as it can lead to rapid and localized corrosion of the anodic metal. In addition to these effects, corrosion can also create safety hazards. Corroded electrical connections can generate heat, which can lead to fires or explosions. Corrosion can also compromise the integrity of insulation, increasing the risk of electrical shock. To mitigate the effects of corrosion on electrical connections, it is important to take preventative measures. This includes selecting appropriate materials for the electrical connections, using corrosion-resistant coatings, and implementing regular inspection and maintenance programs. It is also important to protect electrical connections from moisture, chemicals, and other corrosive agents. Proper installation techniques, such as using properly torqued connectors and sealing connections with waterproof compounds, can also help to prevent corrosion. In summary, corrosion can have significant and detrimental effects on electrical connections, compromising their performance, reliability, and safety. By understanding the effects of corrosion and taking preventative measures, it is possible to mitigate the risks and ensure the long-term integrity of electrical systems. Now let's consider voltage drop calculations. Voltage drop is an important consideration in electrical systems design and installation, as it can affect the performance and efficiency of electrical equipment. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. As electrical current flows through a conductor, it encounters resistance, which causes some of the electrical energy to be converted into heat. This loss of energy results in a decrease in voltage along the conductor. Excessive voltage drop can have several negative effects on electrical equipment. It can cause lights to dim, motors to run slower, and heating elements to produce less heat. It can also cause electronic equipment to malfunction or fail prematurely. Therefore, it is important to calculate voltage drop and ensure that it is within acceptable limits. The voltage drop in a conductor is determined by several factors, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the type of conductor material. Longer conductors, smaller conductors, and higher currents will result in greater voltage drop. Different conductor materials, such as copper and aluminum, have different resistances, which will also affect voltage drop. The formula for calculating voltage drop is typically expressed as voltage drop equals current times resistance. However, in practical applications, it is often more convenient to use tables or software programs that provide voltage drop values for various conductor sizes and lengths. The NEC provides guidelines for acceptable voltage drop limits in electrical systems. It recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. These limits are intended to ensure that electrical equipment operates properly and efficiently. To minimize voltage drop, it is important to select conductors that are appropriately sized for the load and the length of the circuit. Larger conductors have lower resistance and will result in less voltage drop. It is also important to minimize the length of circuits whenever possible, as longer circuits will have greater voltage drop. In addition to selecting appropriately sized conductors, it is also important to ensure that electrical connections are properly made and are free of corrosion. Loose or corroded connections can increase resistance and contribute to voltage drop. Therefore, it is important to use proper installation techniques and to maintain electrical connections regularly. In summary, voltage drop is an important consideration in electrical system design and installation. Excessive voltage drop can negatively affect the performance and efficiency of electrical equipment. By calculating voltage drop and ensuring that it is within acceptable limits, it is possible to design electrical systems that operate safely and reliably. Now let us consider short-circuit current ratings. Short-circuit current rating, SCCR, is a critical parameter for electrical equipment, as it indicates the maximum amount of fault current that the equipment can safely withstand without experiencing damage or failure. When a short circuit occurs in an electrical system, a large amount of current can flow through the circuit, potentially causing severe damage to equipment and posing safety hazards. The SCCR of electrical equipment is determined by testing the equipment under simulated short-circuit conditions. The equipment is subjected to a high current fault, and its performance is evaluated to determine whether it can safely withstand the fault current without experiencing damage or failure. The SCCR is typically expressed in amps and is marked on the equipment nameplate. It is important to select electrical equipment with an SCCR that is equal to or greater than the available fault current at the point of installation. The available fault current is the maximum amount of current that can flow through the circuit during a short circuit condition. It is determined by the characteristics of the electrical system, including the size of the transformer, the impedance of the conductors, and the presence of any current limiting devices. If the SCCR of the equipment is less than the available fault current, the equipment may be damaged or destroyed during a short-circuit condition, potentially leading to fires, explosions, or electrical shock hazards. The NEC requires that electrical equipment be selected and installed in accordance with its SCCR. It specifies that the SCCR of equipment must be equal to or greater than the available fault current at the point of installation. The NEC also provides guidelines for calculating the available fault current and for selecting equipment with appropriate SCCRs. In addition to selecting equipment with appropriate SCCRs, it is also important to protect electrical systems with overcurrent protective devices, such as circuit breakers and fuses. These devices are designed to interrupt the flow of current during a short circuit condition, limiting the amount of fault current that flows through the equipment. The interrupting rating of the overcurrent protective device must be equal to or greater than the available fault current at the point of installation. In summary, SECR is a critical parameter for electrical equipment that indicates the maximum amount of fault current that the equipment can safely withstand. It is important to select equipment with an SECR that is equal to or greater than the available fault current at the point of installation, and to protect electrical systems with overcurrent protective devices that have appropriate interrupting ratings. By following these guidelines, it is possible to ensure the safety and reliability of electrical systems. And finally, remember to always consult the latest version of the National Electrical Code in local amendments for specific requirements and regulations related to electrical installations in your area.